Okay, now it's time for a keynote speaker. We're going to introduce Bill Magro from Intel, and he'll be discussing the use of the new OpenFabrics interface for pulling data and processing it from all the new data coming from interconnected devices.
I think I'm wired up. So, is this mic on now? Can you hear me? Great. Well, good morning, everyone. And I want to thank Susan and the other organizers for inviting me to speak with you this morning. For those who know me, they know I've been involved with Fast Fabrics InfiniBand for a long, long time. And so, in fact, I used to attend this event prior to it being called the OpenFabrics event. I think this grew out of an event that we used to hold, the Department of Energy would host out on the West Coast, right in Sonoma, I believe. Is that right? Went to that for a few years, and then with the formation of IB and then later OpenFabrics. This thing transitioned. It's amazing just to see how it's grown. And sometimes the great places we've picked. This is a great venue, of course. Last year it was in my hometown, my new hometown, Austin. I remember we met in Paris once. That was fun. Should do that again. So I'm here today to talk to you about really three forces that are underway and at play in the world of high-performance computing and other parts of and I'll tell you what I mean by high-performance computing in a moment. It may be different than what you're thinking. And these three forces are really coming together to effect a change that is going to drive, in my opinion, high-performance fabrics into cloud, public cloud and private cloud. That may not be a surprise, but a lot of changes have been underway recently in high-performance computing, and maybe they're not all apparent. And that's what we're going to focus on today with some examples. And I hope when you leave seeing as I do that these forces are coming together and are going to drive this change, and probably quite rapidly. So I want to start by looking at the historical development of the top 500. I got my start in high-performance computing as a computational physicist in 1988, and I was working at NCSA, working on the Cray systems. And in fact, originally my plan for my PhD was to do high-energy physics. I wanted to go up to Fermilab or head over to CERN and wrap coils and discover fundamental truths about the universe. But once I found out there was this thing called a Cray supercomputer, I had to change. So I found a new field so I could get an account on the Cray. And I studied quantum many-body physics. And through the years, I actually had the privilege of working on a wide range of supercomputing platforms. I started on the Cray XMP, YMP, Connection Machine 2, Connection Machine 5, early clusters of workstations with proprietary interconnects from HP, IBM, who am I missing? Sun, Spark Stations, Cray T3Ds, T3Es, and so on through the years. The first IBM SP when I was at the Cornell Theory Center. So I got to see a lot of really interesting transitions in the supercomputing architectures, the rise of PVM and then later MPI, and then OpenMP, and the way it complemented MPI. But what was really amazing is through all those transitions, the development of supercomputing was extremely boring, right? You don't see any bumps here in this. The top line is the sum of the top 500. The bottom line is the number 500 machine. The yellow in the middle is the number 1 machine, where you do see some lumpiness simply because it's a singleton, right? But through all these architectural changes that occurred, it's not reflected at all in these charts. So HPC looks as though it's undergoing almost no changes. Well, one very significant change was the introduction of InfiniBand and the rise of the Beowulf cluster, first with Ethernet and then later with high-performance fabrics, including InfiniBand. My team, in conjunction with NCSA, built what I believe was the first InfiniBand HPC cluster in the spring of 2002 using some Intel 1x InfiniBand connectors. Rob Pennington and his team at NCSA provided the device driver software, and our team went out and got commercial applications like ANSYS and ANSYS and LS-DYNA. ANSYS Fluent, which was just Fluent those days, and LS-DYNA. It's been a while, right, Jim? And we actually demonstrated it in Jim's booth at the IDF conference. About a year later, the first InfiniBand-based machine showed up in the top 500 in the June 2003 list. That came from NCSA. In fact, our collaboration with NCSA, I think, contributed to their confidence in the network and them adopting that and putting that first system on the list. And so while it felt like InfiniBand was starting to get traction, and we saw a new use for it beyond some of the uses that people were seeing, which was around media processing and databases, the reality was that InfiniBand wasn't doing all that well in the ecosystem. There was a lot of competition around the software interfaces, and the industry, actually, from our perspective at Intel, looked like it was on the verge of contracting and maybe even going away. And we found, through conversations with other like-minded individuals, that there was a need to come together and form an organization. And I think that was the birth of OpenIB at the time. The Department of Energy was very active. Oracle was very active. Other industry partners like Mellanox, Topspin, Silverstorm, which was called Infinicon at the time. I'm sure I'm missing somebody. But we came together and said, how can we work as a community to make the software interfaces standard so that people can embrace and use InfiniBand? And then over time, that was the summer, I think, or spring of 2004, when OpenIB was formed. And over the years, the charter of the group expanded. So it's been an exciting journey. You don't see that on here, that first machine or the formation of the organization. But something that's really interesting, in my view, is just how successful this organization has been. We went from one system with what I would call an InfiniBand or an RDMA class fabric in 2003 at NCSA. The most recent list has over 60% of the systems in the top 500 are using networks that are powered by OpenFabrics software. That's quite remarkable, and that's to the credit of this room. All the people who did the real hard work of taking the vision and turning it into code, driving that code out, driving quality, driving adoption, consuming that code in MPI and other and SHMEM and other types of higher middleware, driving all the kernel stuff. So congratulations to all of you. It's been an exciting ride. But I said I was going to talk about changes in HPC, and so far I've only been showing you something that's kind of boring and monotonic. So the first change I want to draw to your attention is if you look closely, the curves that look like they're just rising on this log linear plot, meaning it's an exponential growth. It's actually growing at twice the rate of Moore's law. So that tells you something else is going on besides the CPUs getting faster. And what it is it's been the scale of the systems. And as the systems have gone through each generation of scale, we've encountered hurdles. We saw, for example, the first petascale system with Roadrunner, I think in 98. Is that right? No, 2008. Sorry, 98 was a little bit earlier and closer to an Intel system breaking a previous barrier. But anyhow, 2008. And I think at the time people kind of projected that it was going to be maybe another 9 years. That's how long it took to make the last 3 orders of magnitude. But there is actually a rolling over in the data, and you can see it up there. Things started slowing relative to expectations. So if we're going to talk about HPC and how it's changing, and I said there's really 3 ways, we need to first talk about what do we mean by HPC? I think there's a lot of people in the room are going to have different definitions of HPC, and to follow along today, I think it's really important that we ground on one definition. Whether or not you use that in an ongoing basis is a different thing, but this is the definition Intel's adopted, and I'd like to show you why I think it's useful. So the easiest thing to do is perhaps think in terms of infrastructure. If somebody asks you, what is HPC? You might say, well, HPC is supercomputing. It's about using fast networks and high-performance machines and the right software and luster storage systems and going and tackling the world's biggest problems. It's really about the hardware. But that's not how we see it. Another thing you could do, and this is maybe the easiest way to explain HPC to lay people, this is how I explain HPC to my own family. I talk about what HPC can do, right? You know that hurricane was coming in and they predicted that it was going to stall and then take a right-hand turn, and therefore all these people who didn't look like they were on the path needed to evacuate, right? Or the tsunami coming in, in India. You explain to people that HPC is the way that got done. That's how that safer airplane or that more fuel-efficient airplane or that safer vehicle got designed. Oh, it's interesting. We got notifications coming in on the laptop. So, anyhow, so that's one way to think about it, but that's also not how we define HPC. At Intel, we think of HPC as an activity, and it's an activity that's really characterized by 3 things. We talk about the nature, the intent, and the response to scale. And let me explain that. The nature of the computation, it's got to be something that's truly computationally demanding, meaning it's stressing, whether it be the CPUs, the memory bandwidth, the fabric, the storage system. It's got to be a demanding problem. Otherwise, we can't legitimately call it high-performance computing. We'd have to call it low-performance computing or something else. The second one is actually more important, in my opinion, which is the intent. I can give you plenty of examples of computationally demanding workloads, ones that have driven tremendous innovation in the industry, but their purpose was something very transactional, whether it be databases or network packet processing. What's different about HPC is the intent of the computation. The reason we do this activity is to discover something, to create an intellectual product, right? We're finding out what the weather's going to be like in 12 hours. We're finding out the path of a hurricane. We're understanding how to make subtle changes in a car to make it more efficient and more fuel efficient. And if you've looked at recent Formula One race cars, for example, you'll see that there's a lot of very non-intuitive things that are showing up in designs that are only enabled by HPC because it's a discovery that would not have occurred otherwise. So the intent of the calculation is this intellectual product. And the third characteristic, and I think this is really important as well, is how the problem responds to scale. So if you appropriately apply more resources, do you get a more valuable result? Okay? If I apply more resources and nothing happens, it's probably not a high-performance computing problem. But if I have that weather forecast and I apply more resources appropriately, meaning for the grid size I'm using and everything, and the size of the area that I'm trying to forecast the weather, I can get that forecast faster, right? Less time, strong scaling. That's more valuable because I can take action sooner. Or if I'm already getting it fast enough and there's no additional value there, I can make the problem bigger and I can get a higher fidelity forecast. And that's more valuable, right? And that's the weak scaling, and I apply more computational resources. But this notion of saying I get a more valuable result applies across all HPC problems, in my opinion. And so once you think of HPC in this way, you can now decouple it from where that workload is running. You can run an HPC workload on a non-HPC infrastructure. It maybe just won't get done as fast. You can think beyond simulation and modeling, which is our traditional notion of HPC, and start thinking about other workloads that share those characteristics. So when I say HPC is changing, I'm really thinking in terms of 3 dimensions. The first one is certainly the scale. We talked about that rounding off and the challenges that we see in reaching exascale. And as a result, we're having to give new innovation, overcome challenges we haven't faced before. And as a result, HPC has to change in a really fundamental way there. The scope is what I was getting at just a moment ago, which is this type of problems we consider HPC is broadening. We've thought about simulation and modeling in the past. We need to start thinking about analytics. We need to start thinking about AI and consider those HPC problems. And finally is the delivery. Once you decouple the definition of HPC from the infrastructure it runs on, you can start thinking about HPC in the cloud, for example. I know in discussions I had with many HPC users about a decade ago about HPC in the cloud and the coming relevance of the cloud, oftentimes it was dismissed or people responded as though it was a threat or irrelevant. The cloud, what could that have to do with HPC? And one of my favorite quotes comes from Addison Snell, who says, when I get asked, does HPC compete with cloud, it's like asking whether grocery stores compete with bread. One is a delivery vehicle, the other thing is what you want. And I think that's a great observation that Addison made. So I'd like to talk through each of these in turn and show you how the advances that are happening in each is actually influencing the other and leading to a need for high-performance high-performance fabrics in the cloud. So first, let's talk about high-performance computing's ever-growing scale. So if we go back to, it was the year after Roadrunner, 2009. This was a chart we made internally at Intel. We're just doing some simple math, right, and trying to explain to our own executives and leaders, what is it going to take to achieve that next 3 orders of magnitude? Well, it was pretty plausible and reasonable to think that if you built a system that was about 100 gigaflop processors and there were about 10,000 of them, that one way to get 3 orders of magnitude and get from petascale to exascale would be to do 2 orders of magnitude in the processor and 1 order of magnitude in the scale of the system. But when you start thinking about 100,000 nodes in a network, that becomes pretty daunting. We immediately say, wait a minute, InfiniBand, stops at 48,000. We need to get to 100,000, right? We need to start talking about expanding the address space. Of course, our CPU folks started looking at what is it going to take to go from 100 gigaflops to a 10 teraflop processor. And there are all kinds of challenges there around power and performance and power density, which were still occurring as Moore's law advanced and the density of transistors grew, and thus the power density of the processors grew. So the question is, how do we get to this extreme system scale? And there are a lot of considerations that we looked at. Power was chief among them. A long list of them, including software, jitter, what happens in, system software, application software, and so on. But I'd like to home in on fabrics because that's what we're here to talk about today. So as people tried to push the boundary and really didn't get there, they started changing their expectations. On the last slide, I said maybe we'll get to exascale 9 years later. Maybe we'll get there in 2017, right? Well, 2017 has come and gone, and we haven't gotten exascale. And there have been a lot of reports and a lot of analysis of why and what's needed. There's also been a tremendous amount of investment coming from governments and entities around the world. There's a global race on now to get to exascale. China has set the target of having an exascale system by 2020. The US government has said it intends to have exascale systems in production in 2021. The EU has come forward in the past couple of years and said they're targeting an exascale system in 2022. And even Japan has gotten in on the race with things like the K computer and the evolution of that architecture and that path they've been on to restore their position in leadership computing. So everybody has a different idea of when they're going to get there, but everybody's had to recalibrate. Everybody's had to recalibrate their expectations because of these challenges. So let's talk about fabric and what's needed. I think it was 2013, so 5 years ago, that Paul Gruen and I each gave talks at this OpenFabrics event, and we started talking about what a great job OpenFabrics had done, what a great role RDMA networks had done, but how we were getting to the point that the fabrics were getting so fast that the software overheads were beginning to dominate, and ultimately it would be a barrier to progress, had exascale in mind. Paul in particular talked about other application areas beyond HPC and why some of the semantics of OpenFabrics verbs were going to become a limiter. But at that conference, we talked about why OpenFabrics needed to change. And over the coming year, the OpenFabrics Technical Committee and then the Steering Committee, is it called Steering Committee or is it the board? I can never remember. The board, right? Actually discussed this at length and decided to launch something known as the OpenFabrics Interfaces Working Group, or OFIWIG. And that group has been very, very active and has addressed these challenges, both of the many challenges that we see coming from exascale and other domains. And this is one simple example, is that InfiniBand was not created to run HPC, meaning it was not created for MPI. And as a result, the semantics of MPI and the semantics of the underlying networker don't match. So there's been tremendous work done over the last decade and a half to create sophisticated MPI implementations from many different sources that create higher level protocols and implement what MPI needs given what it has. And the basic premise of our discussion that day was, what if we led with the software interfaces? What if we just wrote the interfaces that the applications, the middleware needed? Wouldn't that free us up to not only run on today's hardware, but also foster innovation? And that exact model has been very, very successful in the PC world with graphics cards, right? You look at what Microsoft has done with DirectX. Every new generation exposes new features, and then the graphics card vendors come along and implement them at their own pace, but implement them at their own pace. And there's always a software fallback mechanism. But now the application software, the games, can move forward. And we're trying to accomplish the same thing with OpenFabrics. So with OFIWIG formed, there really were these four goals. It had to be open source, it had to be scalable and address these problems I was talking about. It needed to be application-centric so that it would foster this innovation and improve the programmability and the access to fabrics. Because I think we all know that OpenFabrics verbs, while a great reflection of the underlying hardware capabilities, are a challenge, and that was a barrier to adoption for many people, and really limited the adoption of InfiniBand, Rocky, iWarp, for example. So more programmability And finally, it had to be implementation agnostic. This is not a new interface for one specific vendor. It needed to be something that really was about what the apps want. So it created a level playing field for everyone to come in and build their best hardware underneath. So in our own, what's happened over those several years, it's been quite remarkable. Things develop much faster than I ever expected. Many people have embraced the new interfaces. Just as one example of our collaboration with Argonne for generation, what's known as MPitch 4, running over OFI. Many different networks and machines are supported. Everything from Ethernet up to the Blue Gene Q, InfiniBand, Intel's OmniPath, existing systems like Cray with the Aries interconnect. We're able to, this shows basically the critical path for a message rate calculation, which is what happens as you go down to the OpenFabrics interface and come all the way back and complete a send, which is going to be your code path for a message rate. And we were able to take that down from well over 1,000 to 200 instructions. And from there, if you start to optimize through static linking, doing locking differently, inlining things, we were able to actually, just as a proof of concept, get it down to 43 instructions from when you make a call of MPI send down to handing things over to OFI, which is the point at which a network that's been built around OFI can actually take that and put data on the wire because of the very thin interface. So it's been tremendous progress. If you look at the numbers on the bottom, it was just shy of 150 instructions to do the send path, the outbound path. We further tuned that in this general case of fully dynamic linked MPIs. So what we've done is we've actually gotten MPI code path out of the way and exposed the value of the fabric. And this is an example of how we're improving the scalability and helping us get to exascale, a key part of our strategy. So there's a long list of fabric requirements. I just gave you one that you need to get to exascale, and you could spend a whole talk on this topic. But if you double click into this notion of consistent, relevant, high performance, there's a sub-list, and I'm not going to read it to you. But clearly, the low latency and high bandwidth we're all familiar with is up there. We need to really eliminate the need for upper layer protocols, and what I mean by that is the artificial creation of software protocols when that's what the application wants, and we could drive it into the hardware. And there's a lot of other things around scalability. Scalability is about maintaining latency as the system grows and not having it degrade. It's about the memory footprint. It's about the challenges we have with many connections, the N-by-N problems, and so on. So I'm glad to say that the application-oriented native transports are down there at the bottom, but the OFIWIG has, I think, really embraced this broader set of needs and introduced a lot of capabilities well beyond, certainly well beyond what I had in mind when I was thinking about this direction for OFA. You can see through the middle libfabric and some of the application-oriented semantics that it has today. Tag matching is the key one, of course, to eliminate that rendezvous protocol I showed you before with RDMA to implement MPI. But there are other things like scalable memory registration, just the ability for an application to actually specify the key as opposed to ask the network, or shared address vectors. These are things that manage the memory footprint locally and also avoid the congestion points that we were getting in the network around the SA. So there's been a lot of innovation. And OFI has really freed us up to examine every single workload and say, what is it it's really looking for and not getting and causing me to put complexity into my software? And how could I extend OFI by adding the right semantic so that over time, if there's enough consumption of that interface, a fabric hardware implementation can come along and implement it. So as you can see across the top, there's a wide range of middleware that has adopted it. This is not a complete list. And across the bottom is a list of the providers that exist today to support a wide range of existing and emerging networks. And I say more under development because there's ones I'm aware of which I can't talk about, and there's others that have been talked about in various meetings. Hewlett-Packard Enterprise, for example, talked about development of a Gen Z driver or provider for libfabric at a recent public meeting. So there's more coming. There's a ton of momentum, and I'd just like to thank everyone in the room for making this real. So let's move on now beyond scale. We talked about innovations that are happening in the fabric and innovations that are happening in the interfaces driven by the primarily by the needs of high-performance simulation and modeling, i.e. exascale. Now let's talk about this new and evolving scope. So one thing we're observing is that there's a whole new wave of computing that's coming along. And it's driven by this deluge of data. It's driven by innovations in artificial intelligence, algorithms, and it's driven by this surge of innovation, which is what happens when people start to get insight and value out of a calculation. It motivates them to go and innovate. And so we're in a very, very rapid cycle of innovation around artificial intelligence right now, and I'm going to give you some examples later. So at Intel, we've done our own estimates. We still think artificial intelligence is in its infancy. Some of our internal estimates are that around 7% at most of servers were being used for artificial intelligence in late 2016 when we did our study. And out of that, only about 40% were being used for deep learning, and only a tiny fraction of those were actually being used for dedicated deep learning with, say, Xeon processors coupled with GPUs. The vast majority of machine learning, which, while still small, or artificial intelligence, while still small, is actually just being done on Xeons or standard CPUs for that matter. So we're going to talk about artificial intelligence and the innovation that's going on there, both not so much in the algorithms, a little bit, but more about how people are approaching it as an HPC problem and why it has network implications. But let's just try to get a handle on how much data is out there that's driving this. I think we all know that at least the most visible uses of artificial intelligence have come out of the cloud providers, right? Whether it be tagging of photos in Google Photos or in Facebook, or analytics that are being run to make product suggestions on something like Amazon shopping site. This is driven by internet data that came from users. That's the top line up there. About 1.5 gigabytes of data per user in 2020 is what we estimate based on a variety of sources. But that data is eclipsed by data that's coming from the Internet of Things. Look at a connected hospital, 3 terabytes. 3 terabytes of data per day. Self-driving cars, if they were driving continuously, let's hope they're not. 4 terabytes of data from the sensors. Connected airplane, 40 terabytes. And a smart factory is just completely eclipses that. If you think of a large-scale factory, like a fabrication facility, or a Tesla, super factory, mega factory for batteries. So the Internet of Things is going to drive all this data in. And it's going in, much of it is going into clouds, public clouds and private clouds. And it's this massive, massive amount of data that's causing almost everyone to say, look and say, well, what data do I have? So when I'm out talking to industrial customers, say in the transportation industry, airplanes, automobile, industrial equipment, they say, well, we've got a lot of data. We've been collecting data, but it's all over the place. How do we get insights? We don't want to be left behind. So if you're familiar with something called the Gartner hype cycle, they would say right now that machine learning and AI are at the peak of the hype cycle. And the hype cycle says that something catches on and people start to know the buzzword, but they don't really know what to do with it. Cloud computing went through this cycle. Then there's this, what they call the trough of disillusionment, as people say, wait a minute, I was excited about the buzzwords, but I don't really know what I'm doing with this. I don't even know if this is real. And then there's this enlightenment piece where it rises again and really becomes a sustained and constant force. Artificial intelligence is going through that cycle right now, and I think everybody believes that it's going to survive the hype cycle. So everyone's trying to figure out what they're going to do. The data they have on premise, the data that's coming in through all the sensors out there into the cloud. How do you make sense of that? How do you gain insights? And if you think again about our definition of HPC, this is an HPC problem. So one thing to observe is that I talked about artificial intelligence and it being an HPC problem. But the other thing that's going on right now with artificial intelligence is becoming a tool for the other domains of HPC. So if you look at climate modeling, this is an area where a simulation can generate tens or hundreds of terabytes of data. And in the past, there's been phenomenological coding that's going in to run the analytics, or even people visualizing the data and scanning it. Can you imagine going frame by frame through a simulation of the entire planet, zooming in on every weather pattern, trying to find examples of severe weather so that you could count them, tag them, and then say, yes, climate change is causing a rise in extreme weather patterns. This is a great application for machine learning. You teach it what an anomaly looks like, an early piece of extreme weather, and then you have the machine examine the data. Similarly, in physics, high energy physics, CERN is in experiments like their ATLAS experiment, which is where this image is from, have again had to build in heuristics to say what is an unusual event. Through machine learning, you can now actually generate background noise, all the known types of particles that will come out of a protonic collision. You can actually generate some things that would be representative of what you think you're going to see when there's some new physics. Shove those all through with tags in supervised learning. And just like you would do image recognition, obviously there's going to be more channels of data here, but feed that through and actually train an AI system to find the new physics for you. So that's very exciting. And autonomous driving is yet another example. If you think about it, I mean, there's a lot of things to be concerned about and think about with autonomous driving, but one of them is you can't wait for Google Maps to get updated by somebody reporting construction. You can't wait for any of those things to make it back. You have to have cars that are collecting data nonstop as they drive and in real time updating the maps for all, whether it be a pothole in the road that's a hazard, a road that's just closed because of a car accident. So cars are going to be generating a tremendous amount of data. And a lot of this data and these events are things that you can't anticipate. So to solve the problem of autonomous driving, you have to build a high-performance computing system. You have to generate synthetic events, and then you have to test how your AI algorithms respond to that and score them based on your objective function, which is don't hit another car, don't kill the occupants, right? Don't go off the road. So all of a sudden, what you've got is AIs, just like you have in computer gaming, running in this massive multiplayer world called the driving infrastructure. This is very much an HPC problem, and one where AI is going to play a huge role. So one thing I didn't mention, but is at the heart of most AI algorithms is dense linear algebra, convolutions, and if you want to run it distributed, a tremendous amount of network traffic. Does that sound familiar? That sounds a lot like the things we see in traditional simulation and modeling. This is another reason that high-performance computing users are some of the folks who are doing the most innovation in how AI runs and takes advantage of high-performance infrastructure. So what we've got is this emerging three pillars of high-performance computing. The traditional simulation and modeling, for sure, where the equations tell you what to do and you generate the data, which you then want to analyze. The analytics, where the data is something you examine and it drives insight. And then AI, where the model is actually being inferred or created out of the data. And we're starting to see not only a hunger for these workloads to coexist on systems, for sure, because you want to use the infrastructure you have, and you know this high-performance infrastructure can benefit these workloads. But you also want to start thinking about integrated workflows. Because when you integrate your workflows, you minimize data movement, right? You want to do in-situ visualization. You want to do in-situ analytics on that common data store. And even then, a highly distributed simulation and highly distributed AI is still going to generate a tremendous amount of east-west traffic within the data center. So that causes us to look at things from a system perspective and say, well, it's great. We've got all the innovation that's happened in Hadoop and later Spark. That rose up. We've got all the innovation of the years of traditional HPC simulation and modeling. Let's just mash those together and get to work. Well, it turns out that these innovations, some of them were born in the cloud and were born on problems that really weren't as demanding. I mean, there are analytics and big data problems that we wouldn't classify as HPC. Why? Because they don't respond appropriately to scale. They're not a hard enough problem, right? Maybe they're generating insights, but they don't meet that other criterion. But the interesting thing that we've seen is that there's these two incompatible ecosystems that have arisen because they didn't need to go together. But as analytics gives you that insight, that intellectual product, what do you do normally? You ask a harder question. And when you ask a harder question, the computational problem becomes harder. And you get a more valuable result, but it gets a little bit slower. And so this cycle has actually been driving people who were initially coming from the analytics side and dismissive of HPC infrastructure. Oh no, I'm going to use HDFS on commodity servers. Ethernet is fine for my problems. they're starting to look over at HPC infrastructure and say, I could use me some of that, right? And then the same thing is happening with the HPC simulation modeling users are looking at all the innovation that's been happening in AI and analytics and realizing how that can advance their science or their engineering, accelerate their insights, lead them to the right simulations to run as opposed to doing a blanket parameter sweep and running them all and looking at the results. Make the whole discovery process more rapid, more efficient. So these worlds are getting forced together, and they're simply not compatible today. So an interesting observation, we'll talk more about it later, is that in the cloud, you can actually spin up a Spark cluster and a Hadoop cluster and a simulation modeling cluster, and they'll coexist simply because there's a common cloud resource manager that none of us get to see sitting underneath, whether it be Amazon's, Google's, Microsoft's, or one in OpenStack, or another. But in order to really get the benefits, we need these things to come together. And on high-performance infrastructure, HPC infrastructure, we're not running those workload managers today. So as a result, the fact that you might be running Slurm or PBS or Grid Engine can actually be a barrier because these frameworks like Spark and Hadoop are actually expecting Yarn. So there's work for this community to do to bring these things together so that they can coexist. New policies, new capabilities for integrated workflows. But the thing we're going to focus on today is really, once you get them there and they're coexisting and they're running, how do you make sure they're actually taking advantage of that infrastructure that's underneath? So I think DK Panda's group at Ohio State has been a long-time contributor to this community and showing the value of high-performance fabrics, focusing on InfiniBand and what it can do for problems within HPC, simulation modeling, and beyond HPC. And they've published benchmarks recently that show both in Hadoop and Spark how you, as the problem size grows, as we said, you very quickly see a dramatic benefit from using the native interfaces from OpenFabrics versus going through something like IP over IB, which is perhaps the best proxy for a TCP IP-based network with equal bandwidth. Sometimes 2 and 3 times improvements at the micro benchmark level, and it manifests as well when you apply it to real problems. One case I saw a 20% improvement in the actual turnaround time of a real workload, still at modest scale by bringing fast fabrics. So that's part of our job, is how to wire these things up and make sure that analytics and AI, as they develop, are taking advantage of high-performance infrastructure and high-performance fabrics. And we'll see more about that later. So what's the latest market data that supports these observations? If you're familiar with Hyperion Research, they're formerly the IDC team that focused on high-performance computing. They spun out when IDC moved to become a Chinese-owned entity. They stayed US-based and are independent now, but they're continuing their work. One of the things that services they've provided to the computing industry for a long time in HPC is forecasts of spending, forecasts of growth. And this is from their recent what's called multi-client study and worldwide server report. And what they say is that overall HPC server growth is projected to grow at 5.8% annually. Right? That's called a CAGR, a cumulative annualized growth rate, just like compound interest. But if you look at the two lines, the upper line is what they call HPDA, high performance data analytics. That's the same as what I was saying, the intersection of big data and analytics problems with our definition of high performance computing, meaning the subset of analytics that can benefit from high performance infrastructure. Doesn't have to be running there today, but can benefit from it. It's growing at a much more dramatic rate. It's growing at 17%. And it's on a path to be a $4 billion server market by 2021 by their projections. Underneath that is AI. They classify AI as a subset of analytics. So this is part of that larger pie. But you can see it's growing at an even faster pace. One of the most interesting things is that only 1.1 billion of that 4 billion they project will be first-time HPC adopters, meaning people who are buying high-performance infrastructure to run these problems. So what this says is there's a very strong bias. Existing HPC users are embracing analytics and AI faster than people coming from the commercial analytics world are embracing high-performance computing infrastructure. So what that says is this community that's driving the fabrics, driving all the performance, all that exascale, those are the folks who are leading. in driving this industry forward. So we're going to be pulling AI and analytics along for the benefit of the community. So now I want to switch to that third trend, which is HPC in the cloud and new delivery. Again, if you stop thinking about HPC as infrastructure and you think about it as the problems you're trying to solve, all of a sudden cloud becomes very interesting. And I want to talk about why. So why would you think about doing cloud for HPC? One example is R&D collaboration. Think of the example I gave before of CERN and the Atlas experiment. You have this massive data coming in. You're clearly doing a lot of filtering, but you're also keeping a ton of data. How do you make that data available to a worldwide network of scientists? Similar problem for the square kilometer array that's in planning, right? Cloud computing provides a platform where everybody can have access, a way to share public data sets. It also gives you access to some of the most powerful networks worldwide. If you're not aware, Amazon, Google, Microsoft have actually laid dedicated networking cables all around the world. In many cases, have some of the best connectivity between the continents. Sometimes much better than the public networks. That can be very powerful if you're dealing with large data sets and you want to enable worldwide collaboration. But the same thing happens even within a given industrial entity who maybe has engineers around the world and wants to take advantage of shortening their time, or take advantage of the fact that these people are up, that someone is up at any time of day, and shorten their time to market. So one group finishes working with a design as the US workday comes to an end, and the European or Asian workers are now picking up on that design and moving it forward and sharing their results. These are examples of how a cloud can actually connect people and move things forward. Another thing is managing surges in demand. I'll talk about that one in a moment. Easy maintenance. Well, computing is never easy, but with cloud computing, there are certain things you don't have to worry about. And if you're capital constrained, you maybe don't want to pay for that infrastructure, and maybe you don't want to pay for that administrator. You're going to let somebody else handle that. The situations where that actually works are fairly limited, but it is still something that shows up in surveys. Access to scale is all about how do I get access to something that's larger than what I have access to. I may have a time-critical project. And then finally, upgrading current capabilities. It may be take a while to get a new system planned, procured, installed, and in the meantime, there's some new technology and you want to try it out. Getting access to it through the cloud can be quite appealing. But I want to home in on two classes of users. The first one is existing users, and then I'm going to talk about new users. And when I say new users, I mean existing and new users of HPC. So this picture I got from Cycle Computing, now part of Microsoft. And they show that the point of this is that whatever size system you install, whether it be 100 nodes, 1,000 nodes, 10,000 nodes, it's fixed size. It's roughly static. Your demand, your utilization, in HPC, it's quite high, but it's never going to exceed your supply. But in survey after survey, companies like Hyperion find that if you go ask users of HPC, how much pent-up demand do you have for your services, there's a lot of folks who have 25%, 50%, 75%, I think even more than that, pent-up demand. So obviously you could just go buy a bigger system, but maybe that's not affordable. But there are times when your supply is constraining the rate of progress on a project. And in those situations, that surge in demand that is unsatisfied really is a missed opportunity. So with appropriate selection of workloads, the cloud can address that. New users have a different challenge. New users really don't know how to set up HPC infrastructure. Think of a small or medium business. If they have an administrator at all, it's likely a Microsoft Windows administrator who's managing email. And with the rise of services in the cloud, maybe they don't have that even. They just have someone who does break, fix, and install of operating systems. How are they going to get into the world of HPC? This infographic on the left from the National Center for Manufacturing Sciences shines a light on the problem. There's 300,000 roughly manufacturers in the United States. 95% are small, 500 employees or fewer. They're providing more jobs than the bigger manufacturers. And they believe that 98% of the products they manufacture are going to be manufactured digitally by 2020, yet 94% of them have not yet adopted high-performance digital manufacturing, meaning using high-performance computing through the CAD, CAE, prototyping, and ultimately validation and test cycles. This is quite scary. And the barriers are not just this administrative issue that I mentioned. Some of them aren't aware or are unable to prove the value of HPC to their management, so they have to start small. But starting small in HPC is hard because you have to buy a system. You have to pay for what seems like a very expensive software license. Ultimately, it will seem like a good value when you see the benefits, but that initial expense of $10 or $20 or more $1,000 to prove a point is really daunting for small companies. So the cloud provides a way to overcome these barriers through essentially push-button creation of clusters on demand, access to pay-as-you-go software licenses, and eliminating the whole administrative and systems expertise problem that they face. So it's natural to ask, if HPC is a set of activities, a set of workloads, and there's many different delivery vehicles, where do the different things fit? Well, I think you can argue quite plausibly that if you build a supercomputer that has, the latest, greatest processors, fabrics, storage, you can run anything. It may not be a great use of that resource, but you can truly run anything, including on a 10,000 node system, 10,000 copies of a serial application to do a parameter sweep. That probably wouldn't be a good use of a supercomputer, but those jobs are great for filling in the gaps in supercomputers. At the far other extreme is public cloud. Public cloud can only run a subset of the workloads of interest, and it's constrained by two things. The horizontal dimension is the requirements for tight coupling of that workload. Remember earlier in the definition of HPC, I said it becomes more value when you appropriately apply more resources. If you just apply more cloud resources to a workload that demands tight coupling, and the infrastructure doesn't have low jitter, it doesn't have good process placement, you're not going to get performance. In fact, you may see performance degradation. So that's what sets this boundary on the right for public cloud. But workloads that do fit, financial services calculations have been early adopters, life sciences have been early adopters, and even some design studies in manufacturing have been early adopters, pushing the limits of public cloud. So the cloud providers, of course, are not going to sit still. They see the demand, and they want to move that frontier. I didn't mention about the vertical axis. The vertical axis is the IP sensitivity. How comfortable are you taking your valuable data sets, whether it be the designs for an automobile, the designs for a microchip, some other trade secret, and putting it out in public cloud? Early on, people were very nervous, but I think with the security breaches that have occurred over the last year, people are getting more and more comfortable that perhaps these cloud providers have access to the best the best security expertise in the industry, and perhaps their data sets will be safe there. That's pushing that boundary up. In terms of ease of use, more and more companies are coming forward with automated HPC orchestration to make it as simple as, say, build me a cluster, and it appears in the cloud. Batch interfaces are appearing so that you can separate the notion of what it is you want to get done from the infrastructure it runs on. AWS Batch is an example of that. And then they're starting to introduce high-performance instance types, including bare metal, starting to think about placement groups, starting to think about how to bring more networking capability in to address the needs and push that boundary to the right to serve a broader range of HPC workload technical requirements. So a couple things that we're seeing, again, back to market data. Our internal analysis is on the left, and we see that up to 30% of HPC use in the way we define it will be in public cloud by 2021. Hyperion on the right has been looking at industrial HPC customers and what are their trends. And they ask the question, which is, in the near term, the next quarter or two, where's your budget growth coming from? Is your budget growing, and if so, where's it going? 20% growth is expected in the near term for public cloud out of industrial users. And this is twice the rate of the budget growth that they're expecting for their on-prem HPC systems and their technical computing desktops. So this is, again, a trend that is very real. And as we talk to people in industrial sites, companies around the world, and commercial HPC users, it's very, very rare for them to not say that they're being asked to look at how they use cloud to augment their on-premise resources and grow capability. But it's not limited to public cloud. If you look at private cloud, the same thing's going on. Again, this is an internal study that Intel did working with many of our users. 69% responded that they're using it for more than 10% of their HPC workloads today. That was a surprise to me. 26%, they're actually running their most important workload in a private cloud. They've made that transition internally. 75%, so the vast majority are expecting their private cloud use to grow, so they're building up that capability. They're not just shipping everything to public cloud. What they're doing is they're taking their internal systems and they're modernizing them by using cloud technologies. And 19% are actually expecting their private cloud use to double over the next year, which means that they're very aggressively driving this transition. It's very interesting. So we've talked about some of these forces that are driving the use of fast fabrics in analytics, in AI, certainly in high-performance computing, simulation, and modeling. But let's talk about some additional forces now in terms of technology trends and innovation that are going to only amplify the need for fast fabrics in the cloud. So the first one is this data from Facebook. I don't know how many people have seen this, but Facebook published this a couple of years ago in a blog. And if you think about the history of the internet, it grew out of services, and as the social networking in particular grew, it was all about how many users you can serve, right? Facebook creating a page and making it visible to their friends, a very localized problem. And Facebook didn't talk about what drove this change, but the early internet systems and data centers were architected really focusing on outbound traffic. How do I serve many, many users? And what's known as east-west traffic, or traffic inside the data center, was not only small, the architecture of the systems aimed to minimize it through load balancers and partitioning traffic. Well, as soon as you build a social network, everybody's connected. You can't eliminate that east-west traffic that's happening inside the data center. And this is the data that Facebook published. They said, look at the growth rate of what our outbound traffic to the internet. It's growing, but not very much. What's really growing is this explosive amount of data inside our own data centers. And they didn't talk about why that's happening, but you can imagine, right? Running tons of analytics, trying to find connections, trying to suggest friends, trying to put the most relevant ad content. All of those things can drive a tremendous amount of this internal traffic, just as we've seen before, as we discussed analytics and AI. Now, the cloud providers tend to be very secretive about their network architectures. They see this as a differentiator. But as part of this post, Facebook actually came forward and published their network architecture at a high level. And Google has done the same thing. I haven't seen Amazon revealing any of their network architecture, but you can imagine that all of them have a lot of innovation. So what do you see in this fabric topology? This looks a lot like an HPC topology, doesn't it? It looks a lot like a fat tree or a class network. You've got all the nodes in groups and racks at the bottom. They're in a one-to-all connection to some intermediate switches, which in turn are connected to a next stage of switches. So multi-paths between nodes, very, very high bisection bandwidth. And Facebook talks about that. They realize that this is so important to support their forward-going scalability of their service that they actually built a dedicated data center in Iowa and basically started with the fabric design and then built the place in the machines and the building around that. That's how important this has become. And Google has also disclosed that their, I believe it's called Jupyter network architecture, their fifth generation network is a class network. So this is happening and it's real. But this is just being driven by the traditional things that happen in the cloud. So what happens when we start adding what's going on with these new use cases? So as I said, the existing high-performance computing users are leading the charge here, bringing these domains together. So you can bet that as the problems of getting Spark and Hadoop to take advantage of a high-performance fabric are solved, being able to harness these things together into workflows and minimize data movement and actually do things in situ with visualization and analytics, the cloud providers will be watching. Because in that slide I showed you before, they realize that they can cover only a subset of the workloads. And of course, to grow their businesses, they need to push those boundaries. So I believe that the cloud providers are going to be watching this space very carefully. They already can run all of these workloads to some degree independently, but as the high-performance computing community drives them to extreme scale, that will be a forcing function for the cloud. So let's just talk about a couple other forces. This is a historical chart of the machine balance, which is the byte to flop ratio. And higher is worse, meaning I'm losing bandwidth relative to the flop rate. So it's really a flop to byte ratio. Over the last 20 years, what you can see is this cloud, these are all machines individual machines that we get from the Stream benchmark site at Virginia, the whole curve has been drifting up, meaning we've lost about an order of magnitude of performance in terms of memory performance relative to the CPUs. And if you've watched, the efficiency of codes has dropped in a commensurate fashion. So what's being done about that? Well, one thing that's being done about that is a new industry, a JEDEC standard called high bandwidth memory. And what this does is it takes traditional DRAM technology, but brings it very, very close to the computer, whether it be a GPU, a CPU, or other processor. It's very dense, it can be stacked, it works with through vias, and it can be mounted directly in package, as shown in this picture. So when you put these things all together, you can get dramatic improvements in memory bandwidth. And what is that going to do? It's going to make every node in the network faster. So obviously that's going to drive higher fabric demands. And I think you're going to see high bandwidth memory starting to permeate the industry anywhere you have computationally demanding workloads. Another innovation that's occurred recently is a new class of non-volatile memories. I show you the Intel example here, which is known as 3D XPoint, but that's not the only one. Hewlett-Packard and many other companies have new non-volatile memory technologies. And as a result, we're having to think about what are the implications of this. Certainly, if you want to put this non-volatile memory out in your network and make it available on the fabric, the numbers are completely different than they've been in the past for rotating media. That has implications I'll show you in just a moment. But there's also interesting semantics that today's networks don't address. And that's why you heard last year, and you'll hear more at this conference, about extending the semantics for persistent memory. Knowing that if I write, not only has it landed in the RAM that perhaps is sitting in front of that persistent memory, but the actual persistent write has been committed. And has it been done in an atomic way, or have I actually corrupted my memory because only a portion of the data was committed and then I lost power to the system? So we have to start thinking about database type semantics and how do we reflect those on the fabric. And you'll hear more about that in some of the talks today. So here's an example that's kind of an analog of the example I showed you a few years ago with MPI, where the software overheads were beginning to dominate the hardware time. So in the old days of a rotating media connected by SAS or SATA, the time to do an access was measured in tens of thousands of microseconds, so tens of milliseconds. As soon as you brought in NAND, that was brought down to around 125 microseconds, but the hardware access time in blue is still dominating the chart. Well, when you now start to attach that with NVMe, you get rid of some of those software overheads. You think you're in good shape again because the software is not consuming a significant part. But when you bring in something like an SSD built on Intel Optane, which is our brand for the 3D XPoint memory, now all of a sudden the software overhead is again dominating the hardware access time because this stuff is so much faster than traditional non-volatile memory. And not on this chart is what happens when you actually create memory DIMMs based on this technology. So it's not even storage. Now you really have to think about getting software out of the way. So fast fabrics and having the right semantics become critical so that we don't build up lots of transactions and software protocols on the wire that obscure the value of this technology. Another thing that's happening is what some call server-defined storage or new storage models. But there's a move to disaggregation, moving from centralized storage to actually spreading the storage out through the network and actually making it accessible in a scalable way. Intel has a project which is part of the exascale computing program and has been focused on solving some exascale problems called distributed asynchronous object storage, or DAOS. And what this is a new distributed object model that allows you to expose many interfaces up, through MPI-I/O, traditional POSIX-I/O, HDFS, but also the types of interfaces that are expected by analytics, such as Spark RDD or Apache Arrow. And the basic architecture is that you spread your storage targets out through the network, right? And every storage node takes a piece of data and replicates on neighbors. So it's using a lot of the same concepts that have grown up in terms of durable storage for analytics, except doing it in a much more scalable way. This puts tremendous requirements on the fabric because there's a ton of traffic, both the access, the pub-sub mechanism, but also the consistency. And And the quality of service of the network becomes incredibly important because you don't want to introduce jitter and disrupt those calculations that are sharing that network. So as a result, some of the things that we're driving and exposing through OFI, again, are going to be very important to supporting the value of new non-volatile memory technologies. Okay. So back to artificial intelligence. I talked about this climate example, the physics example from CERN, and autonomous driving. Let's just jump in and look at how HPC people are tackling the AI problem. So this example is from Surf-Sara, which is an Intel collaboration. This is the National Supercomputing Facility in the Netherlands. I've been working on something called ResNet 50, which is a relatively new residual neural network with 50 layers, and trying to tackle the classic ImageNet 1K problem of image recognition. And the problem that they're trying to solve here is, how do I take advantage of high-performance computing infrastructure to solve this classic AI problem, as an HPC problem? And you can see that through a number of innovations, playing with the model, optimizing the communication, which was done in collaboration with Intel through something called MLSL, the Machine Learning Scalability Library, which encapsulates the communication patterns that are needed in AI. They're able to get really great efficiency, up to 90% here on 256 nodes run at the Barcelona Supercomputing Center. And as a result, they were able, on this system and then later on the TAC system, Stampede, using Xeon Phi and OmniPath, to actually break the world record for this problem by getting it down to 40 minutes. But this is a classic AI problem being run on an HPC system. What happens if we talk about solving an HPC problem with AI on an HPC system? So this is the work I described before, and this is a collaboration among NERSC, Stanford, and Intel, looking at that climate modeling problem I mentioned before, which is detecting extreme weather patterns, and the other one, which is trying to determine new physics as it pops out of the accelerator at CERN and Atlas, and distinguish it from the background. And here what they did is they did a bunch of innovations in the way that the AI is done and the network is constructed and the way the parallelism is exploited. And in the process, we're able to take a 15 petaflop peak machine, NERSC Cori, which is based on a Cray Aries fabric. It's a Cray system and it has Intel Xeon Phi processors, and actually get over 13 petaflop performance running at 9,600 nodes, which is a world record for a real deep learning problem at this scale. So what's really going on behind the scenes? Let me just run through this quickly. You're feeding a neural network from the left with data. There's many layers in that network, and what pops out the back, of course, is the activations or the classifications. And traditionally, you feed the data in, you see what pops out the back, you show it a cat, and out the back it says bicycle. You say, no, that wasn't a bicycle, what you wanted to say was cat. And you feed cat in and feed it backwards. That's called back propagation. And then there's a stochastic gradient descent algorithm that's applied to update the weights with partial derivatives at each layer, and then the layers push the data back forward. That's the back propagation. Well, as soon as you try to distribute it, what I've shown on the left, by feeding data into many copies of the model, what you end up happening is basically you're moving each model forward a little bit at a time, but they get out of sync with each other. So after a batch of processing, say 10 images or however many, you do an all-reduce calculation, an all-to-all, going from one layer to the next. But you also initiate what's called an all-reduce on the way back, which is to take all the updated weights across all the different copies of the model and normalize them, bring them into sync. So there's a lot of collective communication that's going on here. So we've already, as a community, done a lot to take advantage of our learnings from MPI, and a lot of that's encapsulated in various libraries, including the MLSL, Intel MSL that I mentioned. But there are additional opportunities that have implications for the fabric software. Imagine you're in layer 3 and you're doing this back propagation step. You need to send an all-reduce message among all of the different nodes that have a copy of that L3, layer 3 in the network. And you need to start that as soon as you realize that you identified that cat as a bicycle. But then you need to pass with an all-to-all the weights up to layer 2. So the high priority thing is getting that data from layer 3 to layer 2 to layer 1. That's your critical path as shown here. But you've got these lazy messages that need to get to their destination eventually. So this is saying, I need quality of service in the network and message prioritization. The last thing I want is to initiate a collective and actually have it interfere with my critical path. So there's work underway to figure out what are the implications to OFI? What are the implications to the network so that I can keep everything moving very, very smoothly and use the bandwidth that I've got available for the most important thing at a given point in time. That's just one example of getting down into the details, how the rise of machine learning and AI on HPC systems is going to impact fabrics. So I'm going to wrap up with a question of why would cloud providers consider OpenFabrics and OFI in particular for the cloud? And it really comes down to these attributes: performance, programmability, multi-fabric compatibility, flexibility, modularity, extensibility, and innovation. So if you think about the cloud providers, they've revealed very little. They've told you, a couple have told us what their topologies are. They haven't told us is how do they create a safe environment where users are protected from each other and the providers protected from the users, both benign things that occur and malicious things that occur. There's a tremendous amount of technology that's needed to create the illusion that everybody owns the network when in fact nobody except the provider does. Bringing in the capabilities that they know they're going to need, coming from AI, coming from expanding the workload fit for HPC simulation modeling, bringing in analytics, are going to say they have to be very careful about how they bring those in. And I believe that that's going to make it very hard for an off-the-shelf product to come in and solve their needs. Instead, they're going to want to innovate in a way that complements and is compatible with their specific architecture. OpenFabrics interfaces is ideal for that because they're application-oriented interfaces, that gives them flexibility in how they implement or what subset through the modularity of OFI that they implement based on the demand they see in the market. So I think fast fabrics and these three forces, these three forces are coming together and really complementing each other, and they're going to drive a very bright future for HPC in this broad sense and drive fast fabrics into the cloud, both public and private. So thank you very much. So I don't know if we have want to do questions, or should we just move on to the next talk? Who's in charge? Sure. Any questions?
I have a question.
Okay.
Yeah, I have a question, and it's kind of about maybe not exact. It's not about networking specifically, but security in the cloud, because there's. I mean, this is an obvious question, but I'm gonna ask it anyway. Okay. There's a lot of organizations out there who, oil and gas for one, all the DOE laboratories, lots of other places, that can't use the cloud because of security reasons.
That's right.
Do you see a solution there at all?
Yeah, I touched on it a little bit earlier, and let me just bring that back up. So the observation I made before is that there are a lot of folks who don't feel they can put their stuff in the cloud, or traditionally weren't willing to put something very valuable in the cloud, because there's just this security that comes, the sense of security that comes from keeping things close. And of course, I know the government entities have physical security and other safeguards in addition to just network security and software mechanisms. But one observation is that as there have been security breaches lately, we haven't seen the major cloud providers get breached. We have seen other major entities get breached. So I think at least in the industrial world and commercial HPC world, people are starting to get comfortable with the idea that this blue line of what is the my most sensitive IP needs to stay close, close to me, so it's high sensitivity, it's going to stay on my dedicated HPC system, that boundary is moving, but it's a social thing and a mental thing. One thing that the cloud providers are doing is they're out getting security certifications. So I think the easiest one to go look at would be AWS GovCloud, and they'll just rattle off all the security certifications that they've achieved. That isn't going to satisfy everyone, but it is a recognized issue, and I think that line is moving. Thanks. Oh, okay, there's one more question.
When you talk about HPC in the cloud, one of the biggest problems is the WAN speed.
Right.
So HPC in WAN is something I'm looking into right now. I'm interested to know what is the thought process going on in that region, because we need faster data access across the WAN.
No, that's a great point. Excuse me. That's a really wonderful point. And in a deeper dive in HPC in the cloud, that would be the next item on the list. basically a huge barrier is where does your data sit? So some people refer to that as data's gravity. If it's data on-premise, it's extremely hard to get it in the cloud, even if it would be profitable to have access to those compute resources. So what we generally see is where the data is born is where it stays, except for the bursting case I mentioned, where someone might do choose a workload that fits in the cloud, but then very quickly bring that data back on-prem. So as we look at the data feeds from the Internet of Things and so on, as you can imagine, the cloud providers are making it as easy as possible to get data into their cloud and have it stay there. But moving it around is not only time-consuming because of the WAN issues, it's also extremely costly. Cloud providers, for example, if you go look at their pricing, in many cases it's free to bring data in, but it costs you to take data off their cloud or to move it between regions. So they're trying to reinforce the idea of bring your compute to the data. For people who do want to move their data into the cloud, they've made that decision. There are services available. The ones I'm most familiar with, again, are from Amazon. They have something called Snowball, where they'll actually ship a box to you, which is essentially a storage target with a Kindle screen on it that has your address. UPS drops it off. You attach it with one of a variety of interfaces, dump your data, push a button. The Kindle screen flips to a UPS label back to them. The thing is fully encrypted and is shipped back, and they load it in the data center and notify you. And if you have more data, they have something called Snowmobile, which is a tractor trailer that rolls up and attaches to your data center with a pipe. So there really aren't any great solutions right now for moving data into and out of the cloud. And as you know, most people have better downlink speed than uplink, so that's an even greater barrier. So that was a great point. Thank you. Okay. All right. Thank you.